covered
there's so much to write.
many of these actually before, just never written out necessarily in this regard. This would fall nicely with some Gen Chem principles, Honors Chem 1, etc. Not the enthalpy stuff, you haven't seen that before, but over here you have. So we'll try to convince you of that. Factors influencing solubility, I'll have you list them out, and then at some point you should probably maybe Google or maybe look at a PowerPoint or something, but we won't try to re-diagram everything out that's already there for you. The temperature should somehow make sense. So what we're talking about here is this. We do have to define solute versus solvent because that shows up quite a bit. So just get yourself a beaker. Inside of that beaker, let's have pure water. That's going to act as the solvent, the species that's doing the dissolving, right? It doesn't have to be water. It literally can be any liquid, any compound that's in a liquid phase state could be acting as a solvent, or a gaseous phase state as well. But we'll strictly speak to water. We won't do anything else outside of that. What's that? And then the solute is the thing that's being dissolved. And does that have to be one thing? No. It could be multiple things in at the same time. So if that's sodium chloride and you had magnesium chloride in there and you had something else, fine. You have multiple solutes inside of one solvent. So let's just keep this one simple for now. Let's not overcomplicate it. If we have table salt, solid sodium chloride, based on your solubility rules, you would see that that actually forms an aqueous solution. Aqueous solution means that the sodium ions are in there and so are the chloride ions. That no longer do you have this solid down there at the bottom, the ions are breaking up. So that's the portion of this, and we'll come back to this in a moment. When you start talking about the lattice energy, where is that? Here you go. That impacts, will something actually form a solution? The greater the lattice energy, the more unlikely it is to form a solution, right? Or if it does form a solution, the more heat that's given off in the process. All right, so let's just go ahead and put some ions in here. Let's blow that image up. Let's try maybe to shorthand this, maybe a few times, and then we'll, or do in essence one time correctly, and then we'll shorthand it the other time. Why does water orient itself around sodium ion like this? Why does it do that?
We're all still writing.
Yeah.
From what's
But we'll get there. We'll get there. I actually need this to be not discussed right now.
Why?
Yeah.
Wait, actually, can you move the thingy over? No, the
No,
left.
not yet.
No, can you
Not
move
yet.
the left one over?
I will. Yeah. But
Okay.
this is
Margaret!
this is the foundation. We have to define solute and solvent before we can even talk about any other stuff. So just hold off on that for a moment.
Solvent
Yeah.
is doing the dissolving.
Right. But why water? Why does water orient itself around like this though?
Because it's
oxygen is slightly more
Okay.
negative.
The polarity or the distribution of electron density around the water molecule makes these areas slightly negative, slightly positive. Therefore, you have an ion and a dipole interaction together. That's one of your intermolecular forces, an ion-dipole interaction. The more stable this interaction is, the weaker these interactions, which would be called hydrogen bonds, become, right? And you begin to cleave those ultimately. So now we would have an aqueous solution of sodium chloride. We would call this process solvation, the ability of something to dissolve in a solution, solvation. And when that solvent is water, we call it hydration. Do you need to know the difference? No, you can call it solvation or hydration because we don't do anything else. But it just means when water surrounds the ion of interest and puts it into solution, the process by which water stabilizes ions in the solution. Okay. The same thing would be with chloride. Except chloride ions are, so I'll just shorthand it here, right? Draw a few of them. These oxygens are going to be pointed away. They are more negative than the hydrogen components of the atom. So this process of solvation occurs there. Okay. At some point, these two kind of systems collide with each other. The oxygens tend to rip off this water, so this one goes away. Maybe this bond then weakened because this one just formed. And now, can sodium and chloride begin to interact together? Absolutely. And if they will interact, they'll come together, they'll stabilize, but in the next moment, they'll break apart. And that's constantly occurring millions and billions and trillions of times a second, these collisions are. Okay, so that's the big picture item. That's what we generally mean when we put the aqueous notation here, is the process of solvation. All right, so some factors that can influence that. If you heat things up, when you're thinking about this arrangement of sodium and chloride, if you have a water molecule and you increase its kinetic energy, in physics courses, we would kind of define the molecular energy. So this is the translational energy, the energy of motion, moving in some direction, correlates to the mass and the velocity or the speed of the object. If the mass of the water molecule doesn't change, if the factor 1/2 is a constant as well, then the motion, the energy associated with the motion changes as a squared relationship to the speed. So temperature is a measure of the degree of motion when we say this. Back in chapter 2, we tried to define what temperature actually is, and we correlated it to, so in math class, this little symbol here, the non-infinity sign, but it means in relationship to some sort of proportionality is being set up, right? So temperature is directly proportional to the kinetic energy such that the kinetic energy increases as the temperature energy increases. I shouldn't say directly proportional because it's squared, but it's in relationship to. Okay, so why? If you increase the speed at which this water molecule comes, right, is heading this direction, what's going to happen? Literally think of it as billiards. And maybe even better yet, if I have, let's just draw a picture of that sodium chloride. If you have a ball coming at 100 miles an hour this direction, it should make sense that that ball could distort the structure and break and cleave some of the bonds that are there, right? The slower you're going, the less likely that's going to happen. So by increasing the temperature, we're just moving things fast enough that they can collide with the solid and begin to break the bonds. And in essence, if we're looking at the geometric arrangement, remember when you guys saw me try to draw some sort of three-dimensional structure that I can't draw? But there it is, right? Can you kind of see it? Two cubes stuck together-ish. Put right here in the middle, picture that's the middle, the sodium ion. Let's put some chloride ions kind of all around here on various walls and locations, etc. So this is the sodium chloride crystal lattice structure that you would eat. And think about those interactions. You have electrostatic forces of attraction keeping this interaction occurring. But if you heat this up, what does that do to this bond right here? What does that do? If you heat it up, provide heat. It weakens it. But why though? You're right.
Because it's increasing the speed of the
Yeah, it just means that you now have atoms that are vibrating a whole bunch. Now take your kid, hold on to their arm, and have them just start going crazy. It's like, good night, like you're gonna have a hard time holding that kid. In the same way, the more energy you have, the weaker these bonds get. So temperature certainly increases that. Hence why you heat things up on a stove. You're trying to break the intermolecular forces and disrupt the nature of bonding. Agitation, that's a fancy word. What's the real word for that?
vibrating.
Yeah, there you go. Stir. Stir, right? Stirring. When you are stirring something, you're just moving particles past one another more quickly. So if we treat ourselves as the table salt and I am the water, if you're going to stir this solution in the classroom, literally just means I move around. Eventually I interact with Bella, eventually I interact with Vitas, and I just start interacting with the solid particles in the room. So move things around. Honestly, it really doesn't matter a whole lot. You know what I mean? Like temperature matters way more than stirring does. Stir your pot or leave it there for an hour, it's gonna happen. But heat up your pot of water and noodles, wow, that does way more than you just stirring a cold pot of water would, right? Ion modifier, don't overthink that. If we have this solution in here, and we introduce something like magnesium ion in here, that magnesium ion can now interact with the water, and the water is not allowed to interact, or the head of the water, and the tail portion, if you will, the water is not allowed to interact with the chloride as easily. So you're introducing another ion that changes the intermolecular network of bonding occurring in there. Keep going, intermolecular forces, the more forces you have, does it make it easier or harder to dissolve? The more intermolecular forces that are in a solution. Harder, yeah. Just the more bonds that are there, the harder it is to actually end up breaking them. So change that, decrease it, etc. Likes dissolve likes, polar dissolve polar, non-polar dissolves non-polar. What dissolves Ionic.
Ionic?
Yeah, could be, but if you didn't have an ionic solution, polar. Because ionic is just an extreme version of polar, right? Meaning that if you had the actual sodium chloride molecule, let's call it a molecule, if you shift that electron density far enough from being slightly negative and slightly positive, if you actually end up giving those electrons to chlorine, now it's no longer slightly, it is negative and it is positive, right? So it's just an extreme version of that. So fortunately, that means water dissolves salt, table salt, road salt, things like that, etc. Pressures we're going to come back to. I don't want to say too much about it now. Let's take carbon dioxide gas and let's try to put it into this container. When we try to put it in there, it's going to fill the top portion. If we shake the container, some of the carbon dioxide gets mixed into here. But where's that carbon dioxide? Because that's a gas, it's not a liquid. It has a boiling point that's negative 15 Celsius. So that means at room temperature, this water literally would have gaseous carbon dioxide in it. Where's that gas going to go? It's going to escape. We call that vapor pressure. So again, we'll come back to all this later on in the last module, the week before you take the final. So it creates a vapor pressure here. If the top is off of it, then the carbon dioxide continuously escapes through that system, aka you have flat pop. So your pop cans have table salt in them. They also have carbon dioxide, flavorings, etc., acids in there. And when your pop tastes flat, it's because it has no carbon dioxide. So how do you keep the carbon dioxide in there? Put a lid on it. Yep. So you put a lid on it, and then what do you do to it?
You pressurize it.
Yeah, you pressurize it. So if you force these things, these carbon dioxide molecules, to have high pressure, so in essence you add a lot of them, or you change the size of the container, or you drive a piston down on top of them, or you just pump it in at a high pressure here so it forces the carbon dioxide to go into solution, then these will start coming in and out. But the more they go out, the more they come in, the more they come in, the more they come out. And so you have this equilibrium that's established. Back in Gen Chem, you would have had something that's called Le Chatelier's principle. I don't know if I said that right. It's French, Chatelier. Is that how you would say it? Chatelier? French people?
Sure.
Done.
You say this every time.
Do I? Yeah. Lavoisier, Le Chatelier. We're, again, just knowing something can reach equilibrium, and then you can distort that. So you shake the pop can. What does it do? If you shake this now, what's going to happen? Builds up pressure in the can because carbon dioxide is trying to escape. New equilibrium. Okay, let it sit for an hour. Oh, okay. Pop can no longer is dissolved, or no longer has a high pressure. That's good because when the pop's right in your car to the baseball game, if you open that up immediately, psh, goes everywhere, right? But if you wait an hour, it just is the same fizz sensation as before. Why does it fizz? When you open this up and you provide a little hole right there, carbon dioxide escapes. That psh sound is literally a release of that Le Chatelier's principle. You're establishing a new equilibrium. So we'll come back to that too, hopefully, at the end. We'll say more about that coming up. So increasing the pressure increases the solubility of a gas. Saturation. Don't overthink this. If we look at it in terms of the organic molecules that you've been studying, is this saturated or unsaturated if all those are hydrogen? That's saturated. You would call that butane. Okay. If we did something like this, that'd be, 1, 2 butene, etc. But let's just say we'll focus on the degree of saturation. If I put a triple bond in there, what would you say? Butane, right? And that's it. That's what I mean by the organic molecules that are saturated versus unsaturated. However, in terms of solution chemistry, we mean something a little bit different. You remember that rock candy? Remember the sugar on a stick that's jaggedy, and when parents want you to be quiet, they throw it in the back, and then your tongue starts bleeding as you're licking it? You know what I mean? The rock candy?
Okay.
Yeah, you remember that? Legitimately, how you do that is you, oh, snap. Remind me, do it tomorrow.
Should what tomorrow?
That's going to come off, you know it will. Sugars.
Here's a sticky note.
I could. C6H12O6 has some sort of basic general structure that looks like this. So add in several carbons. We call this a straight change, 1, 2, 3, 4, 5, 6. Eventually glucose can look a little different. And I don't remember, we'd have to look it up. On one of these sides are hydroxides, on the other side are hydrogen ions. Depending on which side these hydroxides are on, you get the name. So if this is glucose, then maybe this, if you switch it around to this side, is something totally different. Mannose, galactose, cellulose, etc. So just a general basic structure there. If you add sugar in here, I think the solubility is almost, you can dissolve 1 pound-ish. I think it's 1 pound, we'll look it up, at room temperature. So what is that, 25 degrees Celsius, which is a standard bag of sugar. You can take about that pound, that size of sugar, dissolve it in a beaker of roughly, I think it's 100 mils of water. It's quite a bit. So you get a whole bunch of sugar in here. Let's just pretend each one of these dots is this, right? If you heat this up even more, can you dissolve even more sugar?
Yes.
Yes, because we just talked about how temperature affects that. So heat it up even more. So let's bring that to boiling point. Now you don't have 1 pound of sugar, perhaps there's like 2 pounds. I'm making up these numbers now, but you can put more and more sugar in there. Now you can't heat the water anymore. Why not?
Because it's dissolving the water.
Not dissolving,
Okay.
evaporating,
Sorry.
right? It's at its boiling point. You can't heat water past the boiling point. That's it. So now, whatever you're doing is not going to end up burning the sugar inside. Ultimately, you could produce some caramel out of that process, right? But in essence, if you slowly cool this back down from 100 degrees Celsius to like room temperature, you get something that's called a supersaturated solution of sugar. And if you stick a stick in there, legitimately, just that long, narrow candy stick thingy, it acts as a seeding site for sugar to adhere to. And once it starts that process, it's like a chain reaction. So then more sugar binds, more sugar, more sugar, more sugar binds to that. Otherwise, it would slowly just settle to the bottom and collect on there. Then you pull the stick out, you've got the food coloring, spray it down, add a little sugar to the outside, voila, package it, give it to your kids, sharp, jaggedy edges. So saturated is completely dependent upon, in terms of solution chemistry. Sorry.
Are you okay? I'm
I'm alright, don't worry about it. Just gets me every time, chokes me up.
Oh my god.
It's really an emotional lecture for me, really. Brings back a lot of childhood memories.
Oh my.
He's
Yeah.
choking on the rocket, dude.
Yeah, right?
That's what's happening.
Actually, I tried to swallow at the same time as looking up, and I didn't compensate for the distance of the trachea. Yeah.
What do you mean?
Okay, whatever.
We've all choked on our own spit
Yeah.
before. We all
Why
feel
are
stupid
you
when it
so
happens, so.
Nerd.
The unsaturated, you can add more sugar and still dissolve. More sugar and still dissolve. Saturated, you've added the maximum amount of sugar. If you add anything else, it's not going to dissolve. Super saturated only occurs when you're going through this process of heating up, slowly cooling down, slowly cooling down, slowing down. So most everything, like legitimately, if we asked if your pop is saturated or unsaturated with carbon dioxide, what would you guess? How do you know?
Because the whole thing is with carbon.
Because you could take your pop can and pressurize more carbon dioxide in there, right? And if you did, your pop would become even more acidic, right? So the pH should begin to drop. What was your question?
So would you consider unsaturated all the way up until the point it became completely saturated, like 100% saturated?
Yeah. Mm-hmm.
Okay.
Yep, absolutely. And then anything past that 100% is still saturated.
You wouldn't call it super saturated?
Not unless you go through this process of heating up. Yeah. So if you added more sugar at this point, let's assume it's not super saturated, it's just saturated,
It would just float around, right?
then it actually just sits down here at the bottom.
Okay, yeah.
But if you heat it up, it becomes super saturated.
Then you heat it up, then some of this would come out of the bottom solid phase state into solution. Keep heating it up, you get a little bit more. We've already passed the saturation point for that given quantity of water. Now temperature is the only thing that's affecting our rate of saturation or degree of saturation.
Okay, so by the way, I'm curious. Sugar, you can put 180 grams in 100 milliliters before.
Say that again, 180 grams in 100,
Which is about
in 100 milliliters or 100?
100 milliliters.
So
which is about
almost double the
0.4
amount.
pounds.
So if you had 200 milliliters, we get a $300 to get a pound of that. Nice.
I read somewhere that if you put a like bag of sugar in a ton of concrete,
Yeah,
it
that's-
ruins the concrete.
Oh.
Do what?
I was gonna say.
That's how
Yeah.
Yeah.
I was gonna do that tomorrow, but I'll make you rock candy tomorrow. I'll try
Well,
to
I was
remember.
saying you can, in like a whole gallon of water, you can do 8
Yeah.
pints of sugar.
It's a lot. It's a lot. It really is. Okay, now we have our energy curve. Every single discussion in here, no matter what it is, honestly, we should come back to the energy, the thermodynamic stability. Lowering the potential energy increases, maximizes stability. So let's look at this. Here's the general expression. If something is going to form a solution, so it's going to dissolve into solution, you have to consider the intermolecular forces that exist between two solute particles, right? You have to consider the intermolecular forces that exist between two solvent particles. Then you need to take water and mix it with the solute, and that's the process of hydration. So I tried to diagram that on two different scenarios. One that is exothermic, one that is endothermic situation. And we do always come back to this general curve because it does say a whole bunch for us, right? So we're looking at something like this versus the other one. Okay, so hopefully we can kind of see this. I'll maybe put it in red for a moment. If we have a beginning and we have to go up and now we come back down, you can see that general shape of exothermic. Same sort of thing. We have a beginning, we have to come back down. Notice that our product, if you will, is higher than the energy of our reactants. I am not doing this specifically catered at actual numbers, so it does not matter whether this line or this line are at the same or slightly different heights. Doesn't matter there. What matters is just the general expression, right? Endo versus exothermic. Okay. Why is this always a positive value? So I said it always is an increase in the energy associated with breaking these bonds. Why is that always endothermic?
Because you need energy to break them.
Yeah, that's it. That is a blanket statement chemistry. Breaking bonds always requires energy, right? Doesn't matter if you're endo or exothermic. This is what we're talking about here. If you're going from this region of the curve, I'll do jaggedy line. It always requires energy to break those bonds. Doesn't matter if it's exo or endothermic. All right, that's true here too, right? Because you're breaking the intermolecular forces between water. What bonds do you have to break in water? Go ahead, list them off. Intermolecular forces you're breaking in water. Hydrogen? Dipole. So instantaneous and induced, right? And then that's the basic structure of it. So you have to break those. And then the mixing, notice that the energy associated with mixing is always negative, always pointing down. Why is that?
Whenever you form a bond, it always moves.
There it is, right? Notice this region of the curve is the formation of the bond, so is that one. Doesn't matter whether you're endo or exothermic, forming a new chemical bond always releases energy. Now comparing those, this would be your heat of mixing, and this is your heat of mixing as well. Sorry. Delta H mix of hydration. Okay, you kind of see that working out? What if you had two things? Whose law says this? The magnitude of two charges and the respective distance between those charges influences the energy associated with those. Sorry, what? Schrodinger? Not quite. Coulombs. This is derived from Coulomb's law. Yeah, if you were ever going to take a physics class.
Okay.
Can you stop plugging your own class?
The masses of the Earth and the mass of the Moon, or the Moon and Mars, the Sun and the Earth, doesn't matter, the two masses. The force due to gravity between those objects is dependent upon some gravitational constant and the distance between those two.
Did we do that in physics?
I simplified it to this expression for you. So this derivation is considering these factors. So we did some hand waving.
I had to do that. It was
Did you?
awful.
Yeah.
I had to find one mask and then the other mask,
Yeah.
and then they were giving everything.
Oh, excuse you.
Actually, this might be, yeah, it's just an R.
Wait,
not
so
R
that
squared.
one, the one that you're about to write on now and mess it up as I'm writing it,
Yeah.
that one's Coulomb's.
This one's Coulomb's law, but lattice energy is not directly Coulomb's law, it's derived from it. What we did earlier is looked at this NaCl versus like NgCl2. The magnitude of sodium ion is +1, the magnitude of the chloride ion is -1. The atomic bonding radii between them is something like 10 to the negative 9 nanometers, sorry. So pretty tiny, that's the value of R, the distance between them. The magnitude of magnesium and the magnitude of chloride, different, and the distance is still 10 to the negative 9. So who has the greatest lattice energy? They both have the same bond and radii. Who has the greater lattice energy? Magnesium, because charge matters more than distance does. That being said, if you have let's say the standard heat, or the heat of the lattice energy to be like 3,000, let's say kilojoules per mole. I'm making up these numbers, so if you look these up, they would not be the same. And something that's like 1,500 kilojoules per mole. And let's say this has a heat of solution, this first one, that's like -15 kilojoules, and this one has some heat of solution that's like -50 kilojoules. Which one of these dissolves more easily in a solution?
Top one.
More easily?
Bottom.
Why is that?
Because it wasn't the top one.
Yeah.
The bottom one, because it takes less energy to break through.
Okay, so kind of two parts, the -50 versus the -15, right? -50 releases more energy upon the hydration process. That's indicative that that's more stable than what this is. It doesn't necessarily mean it's more favored, it's just more stable. Now looking at the lattice energies, who's more likely to dissolve?
The bottom
The
one.
bottom one, because it requires less energy to do that. So this is more favorable because this lattice energy is less. And this just proves that versus this. So more to come with that.
Question?
Yeah.
Which lattice energy comes
Top and bottom. Oh, I just made these up. I don't know officially what they are for sodium and
Well, yeah, I know.
What tomorrow we'll do, I got one Google